right. Okay, so welcome everybody for this week's OSU ALT seminar. Today we are very pleased to have Professor Xia Zhou from Columbia University to give us a talk. Let me give a brief introduction for Xia. Xia is currently a associate professor in the CS department at Columbia University, where she is directing this Mobile X laboratory. Before joining Columbia, she was on a faculty member at Dartmouth College, CS. Xia's research area lies broadly in mobile computing, with a current focus on light-based communication and sensing, mobile sensing, and human-computer interaction. She is a stellar researcher in the mobile computing community, and has received so many awards. Distinctly, she is the recipient of this Peace Award, Presidential Early Career Award, SIG Mobile Rockstar Award, and she is also the rising star in networking and communication. And more, impressively, she is also one of the Sloan Research Fellowship owner back in 2017. And many awards. I think without further ado, let's give the floor to Xia.
Great, thank you, Mi. Thank you for the nice introduction. I'm very happy to be here, and also thank you for coming to my talk. Today, I will share with you my journey, our journey actually, of enabling direct air-water communication and sensing with light. So this problem actually came to me from a conversation with my previous robotics colleague at Dartmouth College. And he looks at the use of multiple robots in the water for ecological survey and environmental monitoring. So a big challenge I learned from him is the coordination among the robots. It's very beneficial to have a flying drone above the water that can facilitate the coordination of the robots. But in order for the drone to work efficiently, it has to be able to communicate with and sense the robots in the water. And that turns out to be a non-trivial problem. So there might be some simple options that you might immediately think of, right? So one is to ask the robot to periodically resurface the water to talk and for the drone to sense. But the problem is it will interrupt the robot's current task, so not very efficient. Another alternative, which is also the mainstream method, is to have an infrastructure at the surface, the water surface. So that can be a network of buoys or even a boat. So they basically serve as relays between the drone and the robot. But this method will require a lot of logistic and deployment overhead. Again, it's not an effective approach. So what we really want is a way for direct air-water communication and sensing without any relays on the water surface. So there are many potential modalities that you might be thinking about. So the first one is to use radio frequencies, RF, right? So these are widely used on the ground. Wi-Fi, LTE, we use it every day. However, in this context, the radio signals suffer from severe attenuation in the water. It will lead to very short sensing and communication range. So another alternative is to consider acoustic signals, right? So this is a mainstream method for underwater communication and sensing. However, in the air-water context, right? So this is no longer applicable because based on physics, acoustic signals will be bounced back at the air-water boundary. So it won't be able to provide you this direct link that's going across air and the water. So turns out light is the best candidate in the air-water context. So for one, based on physics, light can penetrate, actually go through air-water interface with very little energy loss. So naturally gives you this bi-directional link between the drone and the robot. Even better if you consider laser light. So laser light has a very narrow concentration of the energy in a given wavelength. So basically you can pick the wavelength with the smallest attenuation in the water and air to enhance the communication and sensing range. So in our experiments, we found green light works the best. So that's around 420 to 550 nanometer. And that's basically giving you the smallest attenuation overall. And also laser light is fast, right? They can be modulated at a gigahertz level. So you can use it to provide very high bandwidth communication between the two nodes. So basically in this talk, I will describe two recent projects along the line. The first project looked at the communication problem using laser light. And the second project studies the sensing aspect. We aim to enable 3D localization of the underwater robot using laser light. So I will begin with the first project. It's called mFlight. So mFlight, the goal here is to address the practical issues to make laser light communication robust in the air-water context. And one practical issue, a major practical issue in this context is really the wave dynamics, right? So water waves, they fluctuate over time, but given the directionality of the laser light, the wave dynamics can easily cause misalignment between the drone and the robot. And from the experiments, we see the link unavailability can go up to around 70% of the time. So definitely won't be usable for any practical applications. Another challenge is related to beam steering, right? In order to support arbitrary location of the robot, the drone will have to steer the laser beam in the full hemisphere. And existing steering methods, they either require very bulky equipment, and also they are also very expensive, so not affordable for a drone to carry. And the last but not least, ambient light is always the enemy for any light-based systems. It's the same here, especially consider outdoor settings where sunlight can be very strong, can be up to hundreds of thousands of lux. So it can easily saturate the sensor and make them not responding to the signals. So how can we deal with all of that, right? So we present mFlight as a generic framework for air-water communication. So it really provides a portable laser communication link that's portable for the drone and the robot to carry. And we also add an ultrasonic sensing element to sense the wave condition and adapt the communication link accordingly. That allows us to achieve reliability for communication. So I will start with some highlights on the communication design. So first of all, at the transmitter side, the main problem is to enable portable full hemisphere beam steering, right? We want it to be fine-grained and really allow you to steer to any location in the space. So the existing gimbal-based method is widely used. However, they have relatively coarse-grained steering granularity is huge. So I don't think the drone can carry that. And it does give you the full hemisphere steering. And another way that you have seen in prior works is to use MEMS mirrors. So these are tiny mirrors that can be electronically controlled. And then by controlling the orientation of the mirror, you can steer the laser beam to any direction. It gives you very fine-grained steering, and it is tiny. The problem is the narrow steering range. So the one we used can only provide plus or minus 14-degree steering range. So that's just too narrow for a practical scenario. So what we propose is to combine the good of the both options, right? So one gives you the full hemisphere steering, but the other gives you the fine granularity. So we try to combine these two methods by using a fisheye lens. So you are probably familiar with fisheye lens already. They are widely used in the camera. These are used to concentrate light coming from the full hemisphere to a very small image plane. Based on the symmetry of light propagation, you can actually use it in the inverse direction, meaning you can steer steer a light ray coming from a narrow angular range and expand it to the full hemisphere. So that's actually what we did here. In order to make it work, we also add a few optic lenses to correct the incident angle for the fisheye. So as a result, as you steer the MEMS mirror in the narrow range, the beam can be basically steered in the full hemisphere once it accesses the fisheye lens. So that's perfect. We are greatly expanding the steering range of the existing MEMS mirror. At the receiver side, the key challenge is to extract the very weak laser light in the presence of strong ambient light. Just to give you a sense on how challenging the problem is, here the x-axis is the wavelength, the y-axis is the relative intensity. So I will show you the energy distribution of the laser light we used, as well as the sunlight that we measured. Right. So the blue peak you see over there is the energy distribution of the green laser. So it's very narrow. Most of the energy is around 520 nanometers. And the purple one is for the sunlight. You can see is having a much wider footprint in the visible light spectrum. And if you take the aggregation and compare the summation of the two, the signal to noise ratio is miserable. It's minus 13 dB. So no way you can actually do anything with that. So how can we deal with it, right? So one difference you see again is the sparsity of the emission profile with laser lights. So basically, if you add a very narrow optical bandpass filter in front of the receiver, then basically you can allow only the light around 20 nanometer to go through while blocking the rest of the visible light spectrum. So as a result, you can actually increase the SNR by multiple factors, right? So in this case, we can increase it to more than 4 dB, and that's sufficient for common or some basic modulation schemes like OOK. On-off keying. Yeah, that's the common one used in light communication. So now with the communication link in place, next let's look at the sensing element, right? So again, the problem is to deal with wave dynamics. Again, wave dynamics can cause misalignment. If you expand the beam, make it wider, definitely can mitigate the issue a little bit, but it comes as a cost of higher energy power consumption, so lower energy efficiency. So what we are trying to do here is to add a sensing element that actively sense the wave condition, and then it steer a narrow beam accordingly to the receiver. So you can see there are two steps. One is to sense the wave, and another is to compute the optimal laser beam direction. So how can we do do the sensing of the waves? Here we use ultrasonic signals. Again, the reason is described earlier, actually, based on physics, right? The acoustic signals will be bounced back at the air-water surface. So what it means is you can actually collect the reflected signal to infer the wave condition. And it's a bidirectional solution, meaning the robots in the water can also use ultrasonic to sense the wave condition as well. So we essentially has an array of ultrasonic sensors. So each sensor can sample the depth to the water, and then you can aggregate those samples and feed them into a wave model. And then you can interpolate the waves and reconstruct the surface. So as an illustration, we used a very simple surface model from computer graphics. It's called bicubic surface model, but this is a generic framework. So for more complicated ways, you can replace it with more sophisticated models. So one issue with the whole pipeline is a delay. As you can see, we have an array of sensors, and if they are all operating in the same frequency, what it means is you don't want them to be sampling the depth simultaneously because they will interfere with each other. But if you let them sequentially sample the depth, it can lead to a very large sensing delay, up to hundreds of milliseconds. So in order to deal with it, so here's just some cute animation to show why this is a problem. So in order to deal with it, we proposed a forecasting method that doesn't need to wait for all the sensor readings to be ready to do the wave reconstruction. We leverage the periodicity of wave movement and basically forecast the sensor reading for other sensors using discrete time Fourier transform. So that allows us to update the wave reconstruction results whenever a single sensor reading is available. So they really boost the reconstruction rate. Yeah, another cute animation to show how this is different now. So now with the wave condition reconstructed, the next problem is to compute the beam direction for reaching the receiver. So here is some notation, right, to signal the outgoing beam from the transmitter, and the R is the refracted beam after refraction. M is a laser beam. So that gives you the incident angle alpha and the refraction angle beta. You also have the norm at the wave surface denoted by the N vector. And the goal here is to minimize the angle theta. So that's the angle between the receiver and the refracted light wave, right? The smaller the theta is, then the better we are aligning with the receiver. And that becomes an optimization problem. Essentially, you want to maximize the cosine of theta subject to a set of constraints. One is the refracted direction based on Snell's law, and also you want to consider the wave norm. This is an optimization problem we can address using gradient ascent. It turns out you can have greedy algorithm that's able to compute the solution within 1 millisecond. So that's fast enough to adapt to a fast wave movement. So now let's look at the actual prototype. So we fabricate everything using off-the-shelf hardware. So this is how the transmitter and the receiver looks like. They are all enclosed with a waterproof tube. And we also have an ultrasonic sensor array 4x4. These are very cheap sensors. The downside is they are not very flexible. You cannot configure the frequency or do any fancy modulation. So we looked at the system in terms of the link performance and the link reliability. We tested two settings. One is a controlled lab setting with a water tank. And another is a swimming pool that allows us to test longer range. And in terms of the throughput, we looked at the system in comparison with two baselines. One is without any steering at all, and another is with steering but without the forecasting method I mentioned earlier. We manually create some water waves by stirring the water. And the y-axis you here shows the throughput measured in megabits per second. So you can see without steering, it's miserable. It's around 2 megabits per second. But with steering and also the forecasting method can give you further throughput gain. We can achieve consistently more than 4 megabits per second throughput in the presence of water waves. So that's translating to more than 80% of the connection ratio. For the range test, right, we have to bring everything to the swimming pool where we set up a tripod to mount the receiver, similarly the drone above the water. And here we tried different combinations of air and the water distances. So here, again, the y-axis is the throughput, the x-axis is the air distance, and we use different color to show different water distances. And so you can see for all settings, we consistently get more than 5 megabits per second throughput, and this is fairly robust. And ultimately, the range is limited by the depth of the swimming pool and the height of the ceiling. So potentially can go further. And the bit error rate is also below 0.01, so it's fairly reliable. Ambient light, right? We mentioned that as a major challenge earlier. In order to see the robustness of the system against ambient light, we considered 2 extreme settings. One is the setting with very dark ambient light, as low as 7 lux. So another is a very bright setting outdoor with sunlight more than 70,000 lux. And here the x-axis shows the distance, the y-axis shows throughput and bit error rate. You can see for both cases, we can achieve more than 6 meter, sorry, too quick. We can achieve more than 6 meter distance with very low bit error rate. So that demonstrates the reliability of the system against ambient light interference. Again, the key is to use the optical bandpass filter to filter most of the energy from ambient light. And another important practical factor is the waves. And I think the evaluation of the wave condition is non-trivial because of the difficulty to reproduce exactly the same type of wave to compare our system to the baselines. So instead of doing that in the real water, we basically build a simulator that's creating synthetic waves so that we can do an apple-to-apple comparison between different schemes. And in order to make the waves realistic, we collected real ocean characteristics in Barbados. So basically we are interested in the amplitude of the waves as well as the wave frequencies, and then use the synthetic waves. We compare our system to the baseline, which is no sensing. We basically vary the amplitude and see the impact on the connection ratio. So you can see a slight decrease in reliability for waves with larger amplitude, but in comparison is doing significantly better than the baseline. And another parameter that we tuned is wave frequencies. So again, for higher frequency, the reliability decreases a little bit, but consistently the connection ratio is above 75%. And in comparison, the baseline without any sensing and steering has a miserable connection ratio around 10%. So it just demonstrates the importance of steering of the laser beam. So this is really a very exciting first step, and there are still open challenges to be addressed. One is mobility. So far we assume the robot is stationary in a location, but in reality, they are not. So how can you address a mobile robot underwater? So that would require the sensing capability for the link to track a moving robot. And then another potential to do is to improve the wave sensing performance. As I mentioned earlier, we are using very low cost ultrasonic sensors. They have limited configuration that allows us to play with. So we can consider more sophisticated sensors where we can configure the frequency or even add modulation to the ultrasonic signals, and potentially can allow us to better address the interference issue to improve the sensing delay and also the accuracy in wave reconstruction. And finally, we'll be excited to take it to the real lakes and ocean for more real world evaluations. It's always exciting to test it in the wild, and especially so in this case. So with that, I conclude the first project and flight. And now I will switch gear and describe the current project on 3D localization of underwater robots. So that's Sunflower. So the problem is to compute the location of the robot in the water, and it's very beneficial for a range of applications. And in this case, the area drone, if the area drone knows the location of the robot, it can more efficiently coordinate their collaboration among themselves. So what are the existing solutions for underwater robot localization? So one thing you can immediately think of is GPS, right? It's widely used. However, GPS waves, again, has very severe attenuation in the water. Basically, it doesn't work underwater. Another option, again, is using acoustic positioning. It is, again, a very popular method underwater. And in this case, you can consider buoys on the surface using acoustic waves to do relative positioning, and then you translate the or transmit the location results using Wi-Fi to the area drone. However, you can see it requires a non-trivial infrastructure setup and also has a constrained sensing area. So basically, we are really interested in the direct localization from the area drone. And that's exactly what the Sunflower system can provide. So this is a quick demo of Sunflower in the swimming pool. So you can see on the bottom right, we show the real-time localization results. And we also overlay that with the ground truth data to illustrate the performance of the Sunflower localization. So you can see as the robot is moving around, we can basically track the trajectory relatively very well. So this is the S for Mobius, actually. So how does it work, right? So the basic rationale is to sense the reflection of light at the drone and then use the reflection to infer the location of the robot. In particular, here we are considering retro reflection. So before we dive into the system detail, I just want to give a primer on retro reflection. So this is very different from specular reflection. So everybody knows specular reflection, you have a signal comes in, and then the reflection will have the same reflection angle as the incident angle, right? But for retro reflection, the reflected signal will be coming back to the source. So that's actually widely used by the traffic signs you see in our daily lives, and that can enhance the visibility of those signs, especially in dark conditions. And here we also use retroreflection for locating the underwater robots. So what are the challenges, right? So the first challenge is coming from the weakness of retroreflection. Remember, the retroreflected light actually goes through air, water, and then back water and the air. So it basically travels twice the distance between the drone and the robot. So it's going to be very weak. How can you reliably sense the weak retroreflected light? That's not clear. Another challenge is ambient light, right? Again, sunlight is strong, and especially in this case, you have such a weak signal from retroreflection. How can we reliably extract that out of the strong sunlight? And last but not least, you also have the sensing skew at the boundary. Remember, the refraction will happen once the light enters the water, and that changes the propagation direction of light. So it will complicate the geometry for you to compute the location. And also waves are dynamic. They can oscillate over time. So it's very difficult to compute the angle directly. So in order to address those, we basically proposed two components. One is a worker component that you can put on the robot. Another is the queen component that you can put on the drone. And the worker component actually contains an angle of arrival sensing system. It senses the incident angle of the refracted light at the robot. The queen has a fiber sensing ring, is able to deal with the weak retroreflected light, and then basically will do the computation based on the angle of arrival data transmitted from the robot using a backscatter channel. So here we optimized the backscatter communication for laser light. So these are the three main elements for Sunflower, and I will go over the highlights of each one. So for the fiber sensing ring, again, the key goal is to sense the retroreflected light, right? So here, again, it's very similar to M-Flight in terms of how we do the laser beam steering. We have the laser dials, a MEMS mirror, and then the fisheye. And once you hit the target, the worker has a retroreflected tag. So basically you can retroreflect the light back to the source. But as you can see, the light is not perfectly collimated, so it has a divergence. So the retroreflected light beam is going to be wider than the original beam. But the sensing region is tiny, right? It's only a single PD. So if you just put a PD along with the fisheye, you are only going to sense a tiny portion of the retroreflected light. And it's already weak to begin with. If you're only sensing a tiny portion, you won't be able to see anything actually. You can put multiple sensors to increase the amount of energy you sense, but will make the system more complicated. So what we did is to propose a fiber sensing ring. So instead of directly putting sensors around the fisheye, we actually use a bundle of the optical fibers. So these are very thin, flexible films or wires. They are perfect waveguides that can collect light signals from a wider area and direct them to photodiodes at another location. So they are perfect for achieving optimal co-location between the sensor and the receiver, the transmitter, which is a fisheye. And also give you the flexibility on how to place the PD, right? The PD can be anywhere because of the excellent wave guiding capability provided by the optical fiber. Another benefit is the aggregation of the energy, right? So I mentioned that earlier as well. So this is a comparison between a single PD and the fiber sensing ring, right? So now we are aggregating energy from a much wider area. So that translates to a larger amount of energy you can actually sense. So that's very beneficial for sensing the weak retroreflected light coming from the underwater robot. So that's the sensing ring. And another element is the angle of arrival sensing at the worker. Again, here, just to put everything in the picture to understand the geometry a little bit better, we have the queen in the air, the worker in the water. So if the worker can sense so basically the worker has a built-in depth sensor that's common for underwater robots. They can sense the depth D to the surface. The same for the drone. The drone typically has a height sensor to sense the height above the ground, in this case above the water. So you have these two parameters already, D and H. And you also know the alpha, right? The queen is steering the laser beam, so you can easily know the outgoing angle of the laser beam. So now if we can also sense beta, which is the incident angle at the worker, then you can basically use geometry to compute the location of the worker and the queen. Sorry for the hiccups on the animation. So how can we do the beta sensing, right? The angle of arrival sensing. And here we use the idea of the pinhole sensing. So imagine you have a 2D image sensor in the back and a pinhole in front of the image sensor. The pinhole is tiny. So then depend on the incident angle of the light rays, it will translate to a particular bright spot the image sensor can see, right? So based on the coordinate of the spot on the image, you basically can do the geometry and compute the angle beta. And it works pretty well and also very portable. So that's basically what we did for the angle of arrival sensing. And the last element is to allow the underwater robot to send the angle, the incident angle back to the drone so that the drone has everything, right? The height, the depth, all the angles, and compute the robot location. So that requires a transmission, a communication channel between the worker and the queen. And we are considering a backscatter channel without actively creating any additional signals. So I think some of you might have heard of backscatter already. So this is a communication paradigm that's not actively creating any signal, but reusing ambient signals to encode data. So in the optical context, right? So here we're reusing ambient light. So the common light considered by the literature is LED light, right? You have LED light in the environment, and then we add a liquid crystal to modulate the reflection, the reflection of the light together with a retroreflector. Then as the light comes in, it will be retroreflected by the retroreflector. Depends on how you modulate or control the liquid crystal, it will result to reflection or no reflection, and that can encode ones and zeros. So that's the basic form of optical backscatter. And you can see the liquid crystal. So in our case, we can consider LED and the PD together on the coin, and then the retroreflector, the liquid crystal modulator will be the worker. So the worker will basically modulate the reflection to transmit the incident angle and the depth value, right? So that will be the traditional way of doing optical backscatter. So you can see liquid crystal plays a major role. And how does liquid crystal work? So this is based on light polarization, essentially. So polarization is essentially the oscillating direction of the electrical field of light in the space. So most of the ambient light is unpolarized, meaning they are oscillating in all different directions randomly. And the linear polarization means the electrical field is oscillating in a single plane. So you have a single polarization direction. And circular polarization means it's oscillating perpendicular to the propagation direction, but rotating around the plane, around the circle, sorry. So liquid crystal basically has two pieces of linear polarizers and with a liquid crystal in between. So as the unpolarized light entering the first polarizer, it will be polarized, right? Only the light with a single polarization direction can go through. And then the liquid crystal is electronically controlled. It will rotate or not rotate the polarization direction. And then what results into either parallel or orthogonal polarization direction with the next polarizer. So that leads to ones and zeros that you can encode for the backscatter. So one problem you can see here is really the use of the first polarizer here. So the first polarizer basically only allows a single direction to go through. What it means is you will lose 50% of the energy from the light source. So that's clearly undesirable. And what we are proposing is to really fine-tune the design for laser light because of the property of laser light. Laser light is already polarized. So you don't actually need to add the first polarizer, meaning if you align the direction with the polarization direction of the laser light, you can immediately go through liquid crystal and then do the encoding of ones and zeros. So that leads to zero loss for enabling backscatter communication. But one caveat is really the alignment, right? So we don't know the polarization direction of the light source, the laser light. That's on the coin. The rest is on the worker. The worker can be moving around, the same for the drone. So you can't assume that they will be perfectly aligned for the zero loss to happen. So in order to deal with the rotation and the orientation variations, we propose to use a weight plate, a quarter weight plate, to convert the linear polarization to circular polarization. Circular polarization is independent of the orientation, so it's pretty robust in the free space, regardless of the movement of the drone and the robot. And then you can use the weight plate to convert it back to linear polarization for the liquid crystal to add modulation. And that leads to the final design where we use the linear polarization at the queen and the worker, but it's circular polarization in the free space to deal with the mobility at both ends. Yeah, so that's the final design. Allows us to support full mobility of the drone and the worker. Okay, so now with everything in place, now we actually can get all the data from the worker. And then again, based on geometry, we can compute the XYZ of the underwater robot at the queen. Yeah. Great. So now let's take a look at the prototype. So here is the queen. Again, the queen really has this flower-shaped fiber ring. That's also where the name sunflower comes from. And basically has these laser optics, the fiber ring, and everything is very small and portable. And for the fiber sensing ring, it's a deeper dive to the ring. It's basically all the fiber bundles. And then you have the MEMS mirror and also the PDs. So here we use the SIPM sensor array for sensing the retroreflected light. Is that the same thing? Oh, the queen. Okay, a deeper dive to the optics. You see every component's inside. Okay, so these are all the weight plates and different components in the queen. And this is a worker. The worker basically contains the angle of arrival sensing with the pinhole, the image sensor, and also we have the liquid crystal to modulate the reflection of the light to do a backscatter communication. So all the components are enclosed in the waterproof tube. Again, they are relatively light and small. So with the prototype, we tested two settings. One is in the swimming pool, semi-stationary setup where the robot is moving around, but the queen is fixed in a tripod. And another is a fully mobile setup where the queen is equipped is basically on the flying drone. So to get the ground truth, we used the conventional method in underwater robotics. They use a fiducial marker. Basically, these are the visual marks, tags that you can add in the environment to facilitate the computation of the underwater robot location. So that requires a heavy instrumentation. So has a limited working range. But in our case, to get the ground truth, that would be sufficient. So here we look at the location accuracy. The x-axis is the error. We show the CDF of the mechanism without refraction sensing, meaning we don't take into account the refraction happening at the air-water boundary. So you can see the blue line, the baseline without refraction sensing, the error is around 20 centimeters. By adding the consideration of refraction, we can reduce the error in half. So in average, the accuracy is around 9 to 10 centimeters. And these basically comparable to existing system, even though the datasheet claims the existing acoustic positioning system, they claim to be achieving error around 3 centimeters, but in reality, you see the error jump to much higher values. And also those only work in the water condition, so it won't be able to support the air-water context. And for the range, we consider the different combination of air-water distances. So the y-axis is the depth, the water distance. The x-axis is air distance, altitude. Here we use the heat map to measure the packet success rate. So the reason we use the packet success rate here is because if the packet can be successfully received by the queen, meaning the incident angle and the depth, then the queen will be able to compute the location of the robot. So success rate basically indicates the localization range. So here, the darker the color, the blue the color, then the higher the success rate. So we can achieve almost 100% success rate for a combination of 2 meter depth and around 2 meter height as well. So the range can go up to almost 4 meters combined. So in the fully mobile setting, again, we put the queen on the drone. So we also have the presence of the wave due to the wind, also the wind from the drone as it's flying around. And here we overlay the localization results from sunflower with ground truth. We can see in general, again, the accuracy is around 9 centimeters. Is sufficient for many robotic applications already. And yeah, and that takes me to the future directions. So there are a few to-dos, remaining challenges to further refine the system. The first issue is reliability. So as you can see, light is easily blocked. So blockage is always a concern. In this case, we'll be interested in looking at the mobility of the drone and the robot to overcome blockage. So if a path is being blocked, we can consider moving either the drone or the robot around to find an alternative path to maintain the link. And the sensing range right now is relatively limited by the power of the laser diode, as well as the divergence of the beam. So to further extend it to tens of meters or even longer, we can consider optimization of the optical circuit to further reduce the divergence of the beam. And also using higher power laser certainly can increase the range as well. Another similar to range, the speed of the tracking is limited by the modulation speed of the liquid crystal. So these are relatively small, up to 1 kilohertz. It will be interesting to look at alternative ways of modulation or better modulation schemes to overcome the bottleneck and achieve faster tracking. And yeah, we will be interested in extending that to multiple robots and really realize the analogy of a queen and multiple workers to allow the flying drone track multiple robots simultaneously and facilitate their coordination. So with that, I want to thank my collaborator, Professor Alberto Christian Lee at Dartmouth, and my 3 PhD students, Ollie, Zhao, and Qijia. I think they are all the heroes behind it. Without them, none of these projects is possible. So big thank you to them, and I will be happy to stop here and take any questions. Thank you, guys.
Thanks so much, Xia, for the very nice and exciting talk. So I think we have a few minutes for questions. Anybody from the audience who has questions?
Hi, so this is Arnav. I want to thank you for a nice presentation. So I have few questions regarding your first part. So do you see any kind of machine learning tools that can be applied specifically when you are like implementing it in the real environment. So there can be some objects which can block. So in order to find the optimal beam direction, I know you are using some optimization and you are using gradient descent as you mentioned, right? So do you see any kind of machine learning tool which can help you to faster the process, or I mean, given the
Right.
past data?
Right. I think the angle of machine learning is certainly interesting. One potential use would be maybe the wave sensing part. So right now we used a simple wave model to reconstruct the wave surface based on the depth samples we collected. I wonder whether the power of machine learning can allow us to do more fine-grained reconstruction of the waves. But the caveat of machine learning is always training, right? You have to have sufficient training data to get good performance. But I think for wave reconstruction, machine learning might be an interesting angle to consider. The actual computation of the laser direction, that alone, because it's purely geometric. So if you know everything, you don't have to use machine learning. You can do the computation to get the optimal direction. Given the fast speed of the algorithm, I don't see an urgent need of replacing that with machine learning.
I see.
But
I see. No,
think-
suppose just to interrupt. So just suppose if the robot is kind of moving, because so we are developing something for optimal beam direction in millimeter wave.
I see.
Right. So this is I mean, for example, for highly dynamic kind of channels. And we are thinking whether we can apply similar technology there.
Right. Yeah, that's interesting. So that's definitely possible. So far, at least in the presentation, I described relatively a simplified scenario, right? You have a stationary robot, and we didn't consider too much about the channel variation. So if we take those into account, yes, there might be interesting things we can do with machine learning. Again, the training is always the challenge.
Right. So do you have any kind of database where you can get those data, or you do not have anything?
We do have a data set. I don't know if it's big enough for machine learning. Also depends on the type of machine learning model you want to try. But if you're interested, we can definitely talk more and see if there are possibilities to explore the feasibility. We can also collect more data and see how machine learning will work. Yeah.
Sure. Thank you.
Sure.
Thanks, Anant. So do you have more questions? Do we have more questions? I thought you have more than one, or not really?
No, I am fine. Yeah.
Oh, okay. Thank you. Any other question from other audience?
I think probably people are hungry for lunch.
Actually, I have maybe two questions. The first one is about the first project. So it seemed to me that one of the key techniques is this forecasting algorithm, or the forecasting scheme for basically forecasting the waves.
Yes.
Seems to me that I'm just wondering how accurate the forecasted results is, because I see that the forecasting give a big boost of the overall performance. Just wondering, how accurate the forecasting should be, or it really does not need too much accurate. So do you have?
Right. So that all depends on the wave motion characteristics. So if the wave is very predictable and very periodic, then the forecasting will work very well, because it all depends on the periodicity of the wave, right? But if you are considering a smaller setting where you can also have echoes from the waves, and they can be added together either constructively or destructively, and then the wave condition will be much more complicated. So in those cases, when the periodicity is less obvious, I think the forecasting will have more troubles. At least in the open water, if you have a very big swimming pool or relatively small wave movement, that's fine. I don't remember the exact accuracy number, but we do have a comparison in the paper comparing the actual waves with the reconstructed one and see the difference. It's pretty small. It might be due to the type of wave we tested. I do think that for more complicated waves, we probably need both more complicated models and maybe better forecasting method to address the complicated interactions between the waves and the echoes of waves.
A follow-up question is, would the forecasting algorithm hurt the performance if it forecasting in the wrong direction, right?
Yeah, it can be, right. So the benefit is you don't need to wait for all the, so if you have 16 sensors, the benefit of the forecasting is that whenever one of them has a new reading, you can start the reconstruction and then update the result and maybe the beam direction. Definitely the caveat is the prediction of the other sensor readings are relatively accurate, right? You don't need to be super accurate given that the beam is not aligned, it also has a beam divergence. So as long as it's in proximity, then it should be okay. I don't have exact numbers on how low the error needs to be for the beam to basically still reach the receiver. But I do feel that there is a trade-off. So on one hand, you do get a gain in reducing the delay, but on the other hand, you do have the imprecise estimation of what other sensor readings are. Yeah, so that's, I don't know the exact number, sorry, but I do feel there's a trade-off there, yeah.
That makes sense. I think probably the last question from my end. In the second project, I see that probably one of the key components is this optical fibers that can collect light sources, right, to get more energy so that you can have more processing power. So how many of these fibers do you normally need? Like, but you know, like, because I think one of the baselines that may not work is that you have only one or two, you know, placed surrounding the sensor, but I assume you need more fibers to collect more, you know, energy to boost the signal noise ratio, right?
Right. So basically, if you look at the figure, let me see if I can find the figure out. So you can surround the fisheye with the fiber bundle. So you can put as many as you like, as long as the retroreflected light will hit them. So I think I have maybe this is a better one to show. So you can see here, we basically has a ring around the fisheye lens, right? It's like a donut shape. If you just look at the ring alone, it's a donut shape around the fisheye lens. Because the light will be coming back to the lens. That's the source of the light, right? So
right.
then you can actually add a donut shape of the ring around the lens, and you can add as many as you like. And then the total amount of energy you can collect depends on the area size of the donut shape, right? You also don't to make it too wide, because it's too wide, then probably you won't get any retroreflected light as well. But that's the general idea. You want to aggregate as much as possible. Yeah.
Yeah, that makes sense. Okay. I think we are a little bit over time, but thanks so much, Jeff, for the very exciting talk. And you know, we learned a lot for this light water communication topic. We want to thank you again for giving a talk on Friday. Thanks so much.
Yeah, thank you. Thank you for having me, and thanks everyone for coming. And,
Sure.
yeah,
Yeah, thank you. And we'll see you everybody next time. Okay. Thank
great.
you. Yeah.
See
Bye.
you. See you.
Bye-bye.
Bye-bye.